Just some final ideas that can help with integration. Symmetry is a big one, if you recognise the curve and odd and even functions. So remember, if you've got an even function, then function negative x equals function x, we know that. So when it comes to integrating, I don't have to go from minus a to a, I can just go twice from 0 to a. That can be handy because 0 is usually an easy number to substitute in. Now, if you think about it, if you've got a horizontal shift happening, and if that symmetry is not about 0 but about a different point, we could still use the same idea. So if it had symmetry around the point C, then the integral from C minus some number to the integral of C plus some number would be equal to twice from that centre point C to C plus A. That's probably not that useful, to be honest. I mean, where the first one was useful is because you were substituting in 0. I mean, you've still got to substitute in two numbers. Where it is useful is odd functions. Because, of course, around the symmetry with an odd function, function negative x to negative function x, we know the actual answer is going to be 0. We don't actually have to do any integrating. So if you've got the horizontal shift happening, then we can say, all right, if I know it has rotational symmetry about a point on the axis, then the integral from a units before that point to a units after that point must be 0. Because you've just shifted that area, which we know cancels out the above and the below. And all we've done is shift it. So the answer is still 0. It hasn't changed. So it would be rare, but you never know. If you do spot it, then obviously it's going to save you some time. It could come in useful, I guess, periodic trig functions. Okay, because, I mean, there's lots of symmetry in trig functions if you think about it. Okay. Here's another one, which is, again, it's a specific situation, but is useful if you can apply it. And if you integrate from 0 to a to the function, you get exactly the same answer as if you substitute into a function a minus x. So everywhere you see an x, you replace it with an a minus x. Now, it's easy enough to prove. So if I've got function a minus x, I'll do a simple substitution. If I let u equal a minus x, the u is minus dx. The limits, when x equals 0, u would be a, and vice versa. So substituting in, I get minus from a to 0 function u to u. I'll swap the limits around, making it positive, but because it's a definite integral, the pronumerals are relevant, because I'll be substituting into it anyway, so that would be the same as function x dx. Okay. Keep in mind with odd and even functions, odd times odd's even, odd times even's odd, even times even's even. If ever you forget, just bring it back to the simplest polynomial you can. So for an odd function, x, an even function, x squared. So odd times odd, x times x, x squared, it's even. Odd times even, x times x squared, x cubed, it's odd. So if you ever forget, just bring it to something really simple and you'll get it straight away. Okay. So sine cubed, integral of sine cubed. You can waste a lot of time here using a technique. You change your sine cubed and work it out. But sine cubed, of course, is an odd function cubed. So it's odd times odd times odd. Odd times odd even. Even times odd odd. It's an odd function. So it's just 0. This one here, x squared root 1 minus x. But notice it's going from 0 to 1. So say it's not that common a situation. But if you notice it, then I can now substitute in 1 minus x everywhere I see x, and it will be the same answer. But that's a heck of a lot easier to integrate, because root x I can just write as x to the power of half. So we do that, add 1 to the power over the power, and we've got our answer. Let's have a little chat about improper integrals. So an improper integral is when we integrate over something which is undefined or something like that. So you're sort of playing with infinities. So therefore we end up using limits to solve it. If a solution exists. It might not exist. Our hyperbola if I wanted to find that from 0 to 1, well, hang on, the hyperbola is not defined at 0. So how on earth do we find the area under a curve? Well, there is no top point. So to do that, what we're actually going to do, because 0 is where the problem is. So what I'm saying is I want to find the limit as n approaches 0 of the integral of n to 1. That integral I can find, the integral from n to 1. And then we have a look at the answer and see if it's possible to find the limit. Now in this case, when we integrate we get a log. So I end up with minus log n as n approaches 0. Well, hang on, I can't find the log of 0. So it's still undefined. Right? So in this case, no good. You couldn't find a value to that particular integral. However, this one, if I was to find the area all the way going up to infinity, so you would think it's an infinite area if you just keep going, keep going. So x e to the minus x squared. So this one here, what I really should write is the limit as n approaches infinity of 1 to n, and find that integral. X e to the minus x squared, well actually that one's just derivative times a function there, so that's not too bad to integrate. We'll end up with minus a half e to the minus x squared. So minus a half e to the minus n squared minus e to the minus 1. Now e to the minus n squared, we can calculate what that is, if you think of the curve, because it's coming down asymptotic to the x-axis. So it would have a value, a definite value of 1 on 2e, that particular integral. What? Now, an idea about area and inequalities. Okay? If you've got 3 curves, and the first curve, which I've called G, second curve F, third one's H. But if G is always less than F is always less than H. So in other words, you're looking at the picture and they never intersect with each other between A and B, but G is always below F is below H. Well, therefore, the integral must also be in that same order because the area underneath would also go in that way. So we're going to have a look at this HSC question. Here's the curve they gave us. We know n's some positive integer. They've told us it's greater than 1. I suppose that's just to make sure that this doesn't get into the negatives, the n minus 1 part there. Area under the curve, and we're going to trap it between the outer rectangle and the inner rectangle, that idea that we've seen before. We're going to show this particular inequality. So we know the area under the curve will be trapped between the inner rectangle and the outer rectangle. The inner rectangle would be 1 times 1 on n, the outer one 1 times 1 on n minus 1, and then the integral we can work out. So integrate that one, we get log. So we now have 1 on n is less than the log of n on n minus 1, less than 1 on n minus 1. We were playing with exponentials. So what I'm going to do first of all is multiply everything by n. Then here we go, I've brought the power in, so it became log of n on n minus 1 to the power of n. Now we know y equals e to the x is continually increasing. It's always going up in that order. So if 1 is always less than the log of that is always less than n, then e to the power of that must also be in that order, because the curve's continually going up. So if the x values, a is less than b is less than c, because the curve's continually going up, the y values must also be in that order. And so the y values then would be e to the power of 1, e to the power of log, which cancels, and e to the power of n on n minus 1. Was that what we had to prove? No, we still got to keep going. What was we? Right. Then we're going to take the reciprocal of both sides. But if we change the, well, not change the sign, change the sign, but if we turn it upside down, the inequality sign changes. And so just making it look a bit neater. There's our answer. Okay. Hey, well, you haven't got the 100 yet. Will we let them have the 100 first, you reckon?
Yes, please, sir.
Oh, I don't know, I didn't get much of a response then.
Thanks.